And we are now recording. Let's go to the current slide. Now, let me go over just only one, it's not major, but just sort of an announcement that you might need to be aware of, and that's the fact that normally on Fridays, I'm on the Birmingham West Campus, 8 to 12, basically, even though I'm usually there earlier and usually there later. Not this Friday. I've got an infusion this Friday, and I don't remember exactly what time, but generally they start about 8, so I'll be at the clinic the whole time that I would be on Birmingham campus, and usually that lasts most of the day, so I won't be going back to campus afterwards. I shouldn't be driving that far, even if I were inclined to go back to campus. So if they give me Benadryl, that knocks me out. All right, so I won't be there Friday. Any questions on anything we've covered so far? And here's Jayla. Okay. All right. Oh yeah, I guess there is one other thing I wanted to bring up. This class started so incredibly well. Of course, it's a great class. Everybody that got that first quiz in really close to right on time, and everybody got that first test taken really close to right on time. But then the second quiz came up, and I still have 2 people who have not turned in, no, 3 people who have not turned in the second quiz. Of course, I haven't seen those 3 people in quite a while, so they may be on the way out. I don't know. Okay, Gary's here. I've got to try to find out if they're going to stay with the course or not, because that's holding it up. The second test, then, a few more people they either haven't taken it or didn't indicate that they completed it. And again, I think I'm preaching to the choir here because y'all are all taken care of, but there's only one person who's regularly attending that I don't know if they're finished with the test or not. And then the third quiz, I've been getting those in pretty consistently, so please keep those coming. All right, so please, well, again, y'all have turned in just about everything, most of you. It's the people who are not here that I don't have time. All right, any questions on anything? Thank you much. Okay. Okay. And there's no rush. Well, I mean, there is sort of one. We're going to finish Module 12 today, and that means the test is coming up Monday. Okay? So, would be a good thing if you did get me the quiz today or tomorrow. That way I can have it graded, hopefully before. Good deal. Thank you. Before the test comes, so you can see what you missed, so you don't make the same mistakes on the test that you did on the quiz, but just don't know it because you didn't turn it in time. Okay. So please try to get that done. All right. No questions on anything we've done so far? Now we're in what they call the work problems sessions. Okay. And these are usually fun. And for some reason, certain math books and mathematicians love this kind of a problem, okay? And it really is not one that I've run into real life that frequently, but they love this kind of problem, okay? Here is the basic formula. The rate at which a worker can work, okay, times the time. And rate usually means time rate. So if you can shovel out 3 corrals of manure in 45 minutes, that's your rate, okay? So many corrals per hour, per minute, whatever. Then multiply that by your 8 hours or 6 hours or 3 hours or whatever, and that gives you what part of the task is completed. Now, most of the time, I'm not really interested in what part of a task is completed, but this type of problem seems to think that's something we're really interested in. Is it, Kayla? Okay. All right. Anyone else come in since I called roll? Okay. So there's our basic formula. Before we get to the focus, there is a sample problem. Okay? So let me go back. I think I'll do this one. Okay? Where is my... Oh, there it is. Stuck in there. Okay, there we go. Here's this is not this problem here. This is not the pen I'm going to use. Okay. All right. This is the problem on page 25 in module 12. For example, if a faucet can fill a sink in 6 minutes, okay? Okay. Can fill a sink in 6 minutes, then in 5 minutes, okay, the faucet will fill what part of the sink? Okay? Something I ask myself every morning, okay? Okay. If the faucet can fill a sink in 6 minutes, that means the faucet fills at the rate of 1 sink per 6 minutes, right? Okay? So that would be 1/6 of a sink per minute, right? It fills 1/6 of it each minute, and in 6 minutes as it's full. So in 5 minutes it will fill, the rate is 1/6 of a sink per minute. Multiply it by 5 minutes. See, units are your friends. They cancel out, and that will be 5/6 of a sink will be filled in 5 minutes. Just what you wonder about every morning, right? Yeah. Of course. Okay. Now, here's another one. A painter can paint a ceiling in 60 minutes. Okay, that's a painter can paint, I'm just going to abbreviate it, PT, a ceiling in 60 minutes. Okay? And here's Q. All right. Anyone else come in since the call roll? Okay? Painter can paint a ceiling in 60 minutes. Right now, we can say what the rate is. The rate is 1 ceiling in 60 minutes, which is 1/60th of a ceiling per minute. All right. That's what I'm interested in. Okay. All right. The painter's apprentice can paint the same ceiling in 90 minutes. Okay? This apprentice used to be on a TV show, I think. Never mind. Okay. Can paint the same ceiling in 90 minutes. That's why he's just an apprentice. Okay? So what will be his rate? This is the rate of the painter. The rate of the apprentice will be 1 ceiling per, I already got a per sign, okay, per 90 minutes, or 1/90th of a ceiling per minute. My units are getting really ugly. Okay. How long will it take them to paint the ceiling if they work together? How long? There's the question. What will answer the question? How long? Is that a distance long? No. That's a time long. So that's going to be the time. That's what we're looking for. The unknown here. Okay? And what was our formula? Rate times time equal fraction of a job. Right? So, we want them to paint the entire ceiling, so that's going to be one job. Okay? That's going to be at the end. So we would have 1 over 60, that's the rate of the painter, times T, plus 1 over 90 times T would equal one job. They've completed the job in that time. We just don't know what the time is. That's what we're looking for. Does that make sense? The rate times the time is the amount of the ceiling the painter can do. The apprentice rate times the time is the amount of the ceiling the apprentice can do, and they're going to finish the ceiling in that time. So we're going to have one job done. Okay? Rather weird. Okay? Now, maybe if you're running a business, this is what would interest you. How do we solve that problem? Say that again? What's messy about it? Oh, I can tell you love your fractions, don't you? You don't find them messy at all. Yes, we need a least common denominator. And here's, since you answered right, Drew came in. Okay. He was just waiting for that right answer. Okay. And what is our least common denominator? Anybody? Least common denominator. Thought I heard something, but I don't hear well. Least common denominator. 180. Exactly. What do we do with it now that we found it? Multiply everything on both sides by 180. There, messed up that pretty little one there, didn't it? So what happens to this first term? 60 will go into 180 how many times? 3 times. In the second term, 90 will go in 180 2 times. So that gives us 3t plus 2t is equal to 180, which is 3t plus 2t is 5t is equal to 180. And how do we solve that? Divide both sides by 5, and that gives us t is equal to, now our t is in minutes because everything was in minutes. I was going to say, whoa, goodness gracious, where'd you go? Okay, there you go. All right. 5 will go into 18 3 times. 3 times 5 is 15. 3 left over. 36 minutes. There we go. Working together, they can go 36 minutes. They can get it done in 36 minutes. Okay? You knew it had to be greater than half an hour because if the apprentice could be able to do it in 1 and 60, yeah, then they would have finished in 30 minutes. But because the apprentice is a little bit slower, it's going to take them a little bit longer. Make sense? Okay, let's see how the book did. Oh my goodness, they wrote volumes, didn't they? Oh, but they got the right answer. Okay, good for them. We're so proud of them. Okay, you see how it works? Okay, read the book. If that helps you understand the strategy and tactics and everything else, then by all means do it. They did it the same way we did. Only difference is they multiplied the 180 by the whole thing. I like to multiply each term by it. It's easier to see. It gets canceled out differently. Okay. Divided out differently. Sorry about that. Okay. So, if any questions on that? All right. Let's clear that, and let's do the one that's actually here. the focus on solving a work problem. Okay? A small water pipe takes 4 times longer to fill a tank than does a large water pipe. With both pipes open, it takes 3 hours to fill the tank. Find the time it would take the small pipe, working alone, to fill the tank. Poor little small pipe having to work all by itself. Okay, but anyway. Now, let's write down what they told us first. A small water pipe takes 4 times longer to fill the tank than does the large water pipe. Okay? What does that tell you about the rate of filling the tank for the small? Okay. Let's back off a minute. Let me ask you a different way. What do we know the least about? Reading the problem. The what? Yeah, the larger pipe. We don't know beans about the larger pipe. We know something about the small pipe, but we don't know anything about the large pipe. Okay? And ultimately, you're going to be looking for time, but not yet. Okay? So let's let the thing that we don't know, that we know the least about, be a variable. Okay? And that will be the rate of the large pipe. Is that okay? The rate of the large pipe. So let's let, now this may not be how the book does it, but this is one way to approach it. Let R, how about R? Is that okay with you? I'll even do RL for large pipe. Okay? Be the rate of the large pipe. Okay? Then, what would be the rate of the small pipe? It's 4 times as fast? No, it takes it 4 times longer. So its rate would be, say again? Okay. If I can run a mile in 25 minutes, maybe, okay, but you can run it in, your rate is 4 times faster than mine, does that mean it's 100 minutes? I don't think so. Okay, I hope not. The station? No, I'm sorry, what? Huh? Johnson? Yes, Kylie, right? Sorry about that. Okay. Okay. Anyone else come in since I called roll? Okay. So what would be the rate of the smaller pipe? The rate at which it fills the tank. RT divided by 4? Yes, it would be R divided by 4. Because it's 1/4 the time. So R sub A divided by 4 is the rate of the small pipe. Okay, and here's Rebecca. Okay. Anyone else come in since I called roll? Okay. All right. With both pipes open, it takes 3 hours to fill the tank. Okay? So, we know that the rate of the small pipe, of the large pipe, times 3, plus the rate of the small pipe times 3 will be 3 hours. Right? Oh, well, it will be, will be 1 tank. 1. Okay? From our formula. Rate times time equals job. So what we have is R, and this is large. I don't know where the A came from. Large. Okay. Rate of the large times T. Times 3. Sorry. Okay. But I'm going to put the 3 in front, if that's okay. I just like my coefficients in front. Plus 3 times R sub L over 4. Okay. Is equal to 1 job. You get the whole tank full in 3 hours. So rate times time, and you're doing both of them together, gives you the whole job. So let's figure out what the rate of the large tank is. Okay? Large pipe, sorry. This is sort of a two-part problem. What are we going to have to do first? Help me, somebody. Anybody?
What's that? What's that?
Right here?
No, it's one of the R. The sub L.
Oh, this?
Yeah.
R sub L. That's the rate of the large tank. Okay. I did that so we'd remember what tank we were talking about. Okay? It's just, you can name it something else. You can do L if you wanted to, not R sub L, whatever. But it's the rate of the large tank. Okay? So, what would be your procedure? What was it on the last problem? Common denominator. And what's your common denominator? 4 is the only denominator. And what do we do with it? Multiply it by every term on both sides. Okay, and what does the first term become? 12RL plus 3RL is equal to 4, right? Now what? Say again? Explain what I just did. Okay, up here, I asked you what do we do next, and so we said find the least common denominator. We found it. The only denominator is 4. What do we do with it? We multiply that by every term on both sides of the equation. This times 4, that times 4, and this times 4. Okay? When you multiply it by 4, 4 times 3 is 12 times RL, right? Here, and this is why we multiply by it, so we can wipe out that denominator, right? And here's Sierra. Anyone else come in and say Chicago? Okay. So this gives us 3RL. And this gives us 4. Is that what you're asking? Okay, got it? See why? Okay. Now what do we do? Add the 12 and 3, and what does that give us? 15R sub L is equal to 4. So R sub L is what? Yes, divide both by 15. It's this one of my favorite fractions of all time, 4/15. Okay. That is the rate at which the large tank can fill the large pipe can fill the tank. 4/15 of a tank per hour. Okay. Okay. Strange. So this is tanks per hour. Okay. Strange. Okay. Now, what we're looking for is the time. This just sets us up here. The time it would take the small pipe working alone without the large tank doing anything to help to fill the tank. Okay? So, we first need to know the rate of the small tank, don't we? I mean, small pipe, I keep calling it tank. How do we get that? Yeah, divide it by 4, okay? So what would be the rate of the small pipe? It would be rate of large pipe, right here, 4/15 divided by 4/1. Right? And what would that be? That'd be the same as times 1/4, right? And sound effects included. The 4's go out, and you have 1/15 of a tank per hour. Okay? So, is it very hard to figure out now how long it would take the small pipe working alone to fill the tank? If it can fill 1/15 of a tank per hour, how long would it take? 15 hours, okay? Take 15 hours to fill the tank. Now, you could set up the equation to do it, but that just came out so easy to see. Yeah, 15 hours. So 3 hours with both of them running full blast, because that large tank is, large pipe can fill it so much faster. Okay? Now that's what we got. Let's see how they did it. Okay? Red-eyed? Any questions before we move on? Now they may have done it quite differently, but I think our way is legitimate. Let's see what they did. Strategy. The time for the large pipe to fill the tank is time T. I think that's what, okay, no, that's not what we did. Okay, so they're doing it a completely different way, but this is perfectly fine. The time for the large pipe to fill the tank is T. This may actually be faster. The time for the small pipe to fill the tank, 4T, because it takes it 4 times longer, right? Okay, now, that's to fill the tank, and it takes them together 3 hours to fill the tank, so 1 over 4T times 3 is 3 over 4T. 1 over T times 3 is 3 over 4T, and that's the time it takes the thing. So you add these two together to get 1. Okay, that's going to be their next step. This was a little faster maybe. The sum of those parts of the task completed must equal 1. So 3 over 4T plus 3 over T is equal to 1. There's your equation then. Now what do we do? This is a different equation, but I think it's going to come out the same. Let's see. I hope so. What do we do now? Now, common denominator, and what would that be? 4T. And what do we do with it? Second, multiply it by every term on both sides. Okay? They do it in a group. I do it by each term. It would be 4T times this, plus 4T times that, plus 4T times that. So what does this first one give us? 3 plus 12 is equal to 4T. Okay? So 3 plus 12 is 4T. Now, add 3 plus 12. 15 is equal to 4T. Divide by 4, and you get 15 over 4T. Well, remember what T was? The time it takes for the large pipe to fill the tank. Okay? Now, what do we do with that? We're not interested in that. We're interested in how long it takes the small pipe to fill the tank. And how long did it take that? 4 times longer. So multiply that by 4, and what do we get? 15 hours. Isn't that what we got before? So both ways worked. Maybe their way was easier to see. Don't know. It could have been. Frankly, I wouldn't have thought of the time for the large tank has been my variable. I would have thought the time for the small tank, because that's what I was asking for. But this works perfectly fine. You just have to remember at the end, that's the large tank, not the small tank. So you have to multiply by 4. Okay? Small pipe working alone takes 15 hours to fill the tank. So if you got plenty of time, like maybe overnight, turn it on, let it fill the tank. When you get up in the morning, as long as you don't sleep too late, you can turn it off before it overflows. Okay? All right, good deal. Now, that's the last thing they do here. They do it in the book. There is a Check Your Understanding 1, and I highly recommend you try to do that probably as soon as you can after class. And then there's 2 practice problems. Do those sometime soon as well. let's move on then to objective 12B. Any questions on this one? I really don't like those kind of problems much at all. They're fine. Say again? Oh, 1 or 2 or 3 or 4. Okay. Okay. We'll try to limit those. Okay. All right. So, whoops. Let's move on to 12.6B, which is the last section in Module 12. And it's not opening. Get out of there. There's. So I'll try to open this time. And here we go. Slowly. All right, we're still in Module 12, and there we have this favorite slide again. And this time we're still in Module 6, or Section 12.6, can't talk, which is application problems. But this time we're at Objective 12.6B, which is solve uniform motion problems. Now these kind of problems make a lot of sense, okay? The others do too if you're filling tanks or sinks or whatever. But painting ceilings, you know, that may be quite useful to you. But everybody travels, they move, they displace themselves. A car, which most people ride in every now and then, that travels constantly, that may be on cruise control or something like that, in a straight line. Okay, that would be out west somewhere, I think. You just drive the same direction forever and don't get anywhere. 30 miles per hour. Goodness gracious, that would be boring, wouldn't it? Is in uniform motion. Now, it doesn't mean just at 30 miles per hour. MPH is usually miles per hour. Anytime you're going at a same speed, straight line, no deviation, no turns, you're going in uniform motion. So when an object is in uniform motion, its speed and direction do not change. Okay? And by the way, I'll just throw in a little bit of physics here. You could simplify that saying the velocity doesn't change, because velocity is a combination of speed and direction. Velocity is a vector quantity. We're not getting into that. Okay? The basic equation used to solve uniform motion problems is distance is equal to rate times time. And you know what? This works even if you turn. You know? It still works even if you turn. As long as you're going at a constant speed, rate times time is equal to distance traveled. Displacement may not be, but distance is. An alternative form for this equation is written by solving the equation for time. So what we do, we divide both sides by the rate, and you get time is equal to distance over rate. Hey, there it is. Okay? Now, I just said that. Let me show you that. If you're trying to solve for time, oops, let me get my pen back. Then we divide both sides by rate. Rates go out here, and time is equal to distance over rate. Of course it is. Now, you could have solved for rate. Rate is equal to distance over time. So there's 3 equations that basically say the same things. They're equivalent equations. Now, I don't know if I should do this to you, or for you, but when I went to some Navy schools, and I've gotten this Buddhist before, okay, they did this kind of, I think I've even shown you this before, haven't I? That little, oh, the 10 o'clock scholar, okay, all right, Pablo's here, okay. I don't know if you find these helpful or not. You can either use triangles. Have I shown you this before? I thought so, right? Or a circle. And you did it in high school too? It's what? Triangle or circles, either one, whichever you prefer. I like triangles better. When you have something like this, distance equal rate times time, this is your division line, that's your multiplication line. Since you know rate is multiplied by time, put the rate down here, the time here, that leaves this for the distance, right? Now, if you're trying to find any one of these, like time, cover time, and that's distance divided by rate, right? If you're trying to find rate, that's distance divided by time. And if you're trying to find distance, it's rate times time, just like we had here. Now, if your formula is like this, you put distance on top, rate in the bottom, and then time has to be down there too. You get the same way. Either circles are, nothing changes, it's just which shape you prefer. Distance equal rate times time. Now, that way, it takes a lot of the thinking out of it. And in the Navy, sometimes that's a good, I'm sorry, I didn't say that, did I? Okay. So, this form of an equation is useful when the total time of travel for two objects is known, or the times of travel for two objects are equal. Okay? So this is going to complicate the problem a little bit, but it still works. Still works. Okay? Now, let's see. Okay. Let's do their sample here. The speed of a boat in still water is 20 miles per hour. Speed of the boat in still water is 20 miles per hour. I like to write it that way because MPH, quite often M means meter, and people get confused. That means miles per hour, so I put MI per hour, okay? The boat traveled 120 miles down a river in the same amount of time it took a boat to travel 80 miles per hour, 20 miles down the river in the same amount of time it took the boat to travel 80 miles up the river, okay? So here we have the boat going down the river, okay, and the boat traveled 120 miles downriver, okay, in the same time, we don't know what it is, same time it took the boat to travel upriver 80 miles. In that same time t, okay? Find the rate of the river's current. So we know the speed of the boat itself, but not with the current, okay? So find the rate of the current. That's what we're looking for. R sub C, rate of current. I can't write. Now, which way you reckon the current's flowing? Upriver or downriver? Downriver. You're absolutely right, because it went further. So the current, this is your R sub C. Okay? Now, we know the speed of the boat, which is the rate of the boat, and you know there's a current. So this time t, we don't know what time t that is, but RB, which is 20, plus RC, which is current, times t equals 120 miles, right? Rate times time equals 120 miles. So let's do that. Rate of the boat is 20 plus RC. Is that what we're looking for, isn't it? Yeah, rate of the current. Times t is equal to 120. Okay? I'm putting the miles there, but we probably won't need it. But when you're going upriver, it's 20. That's the speed of the boat minus RC, because now the current's going against you, times t, same t, is equal to 80 miles, right? Rate times time equal distance, right? Agree with that or not? Does it make sense? The rate's working against you going upriver, so you have to subtract it from your 20. Where it's going downriver, you add it to the 20 because you're going faster. Right or not? Okay? So we can basically eliminate the t. We don't know what it is, but it really doesn't matter. It's the same in both cases. So let's do t for the first case is 120 over 20 plus r sub c. And in the second case, t is equal to 80 over 20 minus rc. Right? I mean, that's what you got. If you divide this, you get this one. Divide this, you get that. Right? And those are the same t's. They said the same time. Okay? So there we have our equation. Can I erase my sort of ugly drawing? Y'all agreed it was ugly, huh? Oh, I'm hurt. Okay. Okay. Did y'all need it any longer? Too bad. Okay. All right. So let's set them equal to each other. 120 over 20 plus RC is equal to 80 over 20 minus RC. Okay? How do we solve an equation like that? Yes, very good. You remember how to solve a proportion, cross multiply. So let's multiply these two. That'd be 120 times 20 minus RC is equal to 80 times 20 plus RC. Okay? Let's multiply and see what you get. Help me. Anybody? Please help. I'm drowning in the river. 2, 4, 0, 0, minus, help me, 120 RC. I get thirsty thinking of that. Never mind. Okay. Y'all don't even remember what RC. Oh, you remember. All right. What's the next one? What's that one? 80 times 20? Anybody? Come on. You don't need those black boxes. 1600 plus 80 RC. All right. Now, what's our next step here? Anybody? Does everybody agree we got there? Yes. What do we add? Second? Yeah, you got to get them all on the same side. Now, which side would you like what? Okay, I have a little preference. I always like my unknown to have a positive coefficient. This has a negative, so I'm going to add the 120 RC to this side, and since I'm doing that, I'm going to subtract the 1600 to that side. Just because I'm lazy. I don't like to mess with. Is that me or somebody else? Oh, okay, good. Okay, throwing things around now. So let's add 120 RC here, and of course we'd have to add it here too. And let's subtract the 1600 here and get it over here. Now, if you want to do this in 2 steps, do it in 2 steps. I'm just running out of room, so I'm trying to conserve space here a little bit. These add to 0, those add to 0. And what do we have now? 800. Whoops, I started to write something. Whoop, no. Okay. That. Okay. 800 is equal to, second, 200 RC. Okay. And then what do we do to get RC? Divide by 200. And that's a pretty easy division. That would be RC is equal to, second? You can do it. 4. And that would be 4 miles per hour. So the rate of the current is 4 miles per hour. Okay. Now, to me, the keys here are let the variable be what you're looking for, right? Now, in the last one, we had to have 2 variables in it, a t, which we didn't know, and whatever the other rate was. But, you know, we dealt with that because the 2 t's were the same. We eliminated those and then solved for the one we had. This one, we didn't even have that problem. Oh, no, that was this problem. Oh, the last one we had, well, so eliminate any, try to get settled in on the one you're looking for. Eliminate any of the extras, which that one would have been. Let's see how they did it. Now, this is on the slide set. This is in the book. They did say that the distance downriver was 120, which we knew. And the rate was 20 plus R. They didn't call it RC, they just called it that. So the time it took was 120 divided by 20 plus RC. Okay? That gives you the time. And the time upriver would be the distance divided by rate. So they did it. They got there a little differently, but they came up with the same 2 equations right there, that one right there. Those 2 were equal to each other because the times were equal. They came up with R is equal to 4 miles per hour, just like we did. Okay. Any questions on that? So let's erase that. Is it all right to erase? Anyone still have any questions? Ask if you got them, because they're going away. Okay. There it went. Okay. Now we're ready for our cyclist. A cyclist rode the first 20 miles of a trip at a constant rate. For the next 16 miles, the cyclist reduced the speed by 2 miles per hour. The total time for the 36 miles was 4 hours. Find the rate of the cyclist for each leg of his trip. Okay. And again, here we ask ourselves, which rate do we know the least about? The first rate or the second rate? Well, actually, we know more about the second because it's 2 less than the first rate, right? We all know what the first rate was. But we know the second rate was 2 miles per hour less. So let's let the one we know the least about be our unknown. You want that to be R or RF for first rate or something like that? RF, okay. So let's I usually like to find the rate of the cyclist for each leg. Well, which one do we want to name? Let's name the first one. Let RF be the rate for the first leg. Okay? Okay. Then, can anyone tell me what the rate for the second leg will be?
16.
Say again? Okay. Use the RF, I mean. For the second leg, next 16 miles, the cyclist reduced his speed by 2 miles per hour. So if his initial speed was RT or RF minus 2 would be the rate for second leg. Got it? Does that make sense? And then when we finish the problem, we'll solve for RF and then subtract 2 from it and have for R for the second leg as well. Okay? Because that's what we're looking for. Actually, the rates of the cyclist for each leg. I would have put an S on there. Okay? But you said each leg, so it's right, this singular. Okay. All right. Now, what's our formula that combines rate, distance, and time? Okay? Okay. So for the first 20 miles, we must know the distance, and we at least name the rate. So we could calculate time, couldn't we? So the time for the first, TF, would be what? How is that related to distance and rate? Remember our formula? Give me the formula. I want to write it down somewhere. Distance equal rate times time, right? Everybody agree with that? We're looking for time, so time is equal to distance over rate. Okay, so our distance for that first leg was 20 miles. Y'all are clever, okay. And the time was, and the rate was? RF. Okay, it can be a variable. Okay, now the time for the second leg was what? Its distance over time. What's its distance? 16 miles divided by its rate. What was its rate? RF minus 2. Okay? And these are not the same times, but what do we know about the times? 4 hours. So we know that 20 over RF plus 16 over RF minus 2 is equal to 4. Don't we? There's an equation in one variable. It's in a nasty location, but we have the equation in one variable. Can we solve it? Common denominator, and what would that be? Well, R won't go into that, will it? But RF minus 2 won't go into that.
So you have to add.
No, not add.
Subtract.
No.
Cross multiply.
No, just multiply. Multiply them together. The common denominator is the product of those two denominators. If we don't know what, okay, if it was 3/5 and trying to add that to 4/12, okay, 5 and 12 don't have anything in common. So you have to actually multiply them together to get something like common, right? That would be 60. Yeah, okay. 60 would be the common denominator. Y'all do that all the time. 1/3 plus 1/2, okay? They have nothing in common, so you just multiply them together, right? Okay, tell me, okay. 1/2 plus 1/3. What's common denominator? 6. How'd you get it? You multiplied them together. That will always give you a common denominator. It may not always be least common, but this has nothing in common, so you have to multiply them. So the least common denominator here is going to be RF times RF minus 2. Okay? And we multiply that by here, RF times RF minus 2. And we multiply over here by RF times RF minus 2. Okay? In this first term, what goes away? The RFs do, and we have 20 times RF minus 2. Right? Yay or nay?
Yes.
Yay. Oh, yay. All right, got it. Okay, yeah. Now. All right. In this one, what goes away? Second term? RF minus 2 goes away. So that leaves us a plus 16 times, oh, that's a 20 there. How did that become a 2? Y'all messed up, didn't you? Really bad. Okay. All right. And that would be 16 RF, right? That's equal to, now here I would multiply those two together. In fact, multiply all three of them together. 4 times RF is 4 RF squared. Minus 2 times 4 times RF is minus 8 RF. Right? Yay or nay? Agree or not? Okay. Did I lose anyone here? Yeah, okay. 4 times RF is 4RF times RF is 4RF squared. 4 times RF times a minus 2 is minus 8 RF, right? Just multiply. This is the coefficient, 4RF. Take out the parentheses there if you need. Okay? Just take them out. Throw them away. You're not using them anyway. Okay? That's 4RF times RF minus 2. Does that make it easier to see? Okay? 4RF times RF is 4RF squared. 4RF times minus 2 is minus 8 RF. Right? Okay. So that's the right-hand side. Let's clean up the left-hand side. What would that be? Let me get my pen back. Okay. 20 RF, help me, minus 40 plus 16 RF is equal to 4 RF squared minus 8 RF. Okay, now what would you suggest we do? Combine like terms over here, and that would be 36 RF minus 40 is equal to 4 RF squared minus 8 RF. For some reason, the pen's not writing very well. Neither am I. Okay, I'm going to need some more room. What's that? Okay. What I'm going to do, I think, is erase this part here. We've already used it, so I'm going to erase this. You still have it written down. You don't have to erase it, okay? But I'm just going to erase this part here to make it easier to read and see. Okay. Probably could erase this up here, too, because we already dealt with that. Okay, and we can erase some of this, too, just because it's messy. Okay, but messy. All right. All right. Now, let's focus on this equation down here. We're going to rewrite it up here. Okay? And where do I like to, what do I like to have positive? My leading term. What's the leading term? 4RF squared. Okay? So I want that by itself. So I'm going to write it down first. So I'm going to write that whole thing down just because I don't want to confuse you. 36 RF minus 40 is equal, you don't have to write it again if you already got it, 4 RF squared minus 8 RF. Okay? So I want to focus on this one, get everything over there with it. So therefore I will subtract 36 RF from this side, which means I subtract 36 RF from this side. These are getting to be some pretty big numbers. Then I'm going to also add the 40 here and add 40 here. Now why am I doing all that? Because I have a quadratic. And with quadratics we want everything on one side, 0 on the other side. And that's what we're going to get. So this produces, I'm going to switch sides now, 4 RF squared. When you add these two, you get minus 44. Is that right? RF. Y'all help me. Right? When you add those two, plus 40 is equal to 0, because everything over here added to 0. Right? Now, what do you do with that? Factor! And what would you factor first? Yes, factor out that 4. Who wants to haul that around? So factor out a 4, and that would be RF squared minus 11RF plus, say again, plus 10 equals 0. Now, what you're asking we ought to do with that 4? The good news is it's an equation. So what we can do is divide it away. Okay? Just get rid of it. Because, see, 4 can never equal 0, so that's not going to be part of our solution. So we just divide it away. If 0 divided by 4 is 0. That's a 1. So we're just left with that. All right? Now I'm going to take that up here. RF squared minus 11RF plus 10 equals 0. We're going to hope that that factors. Can y'all hope with me? Okay, what would be the first factor? Only possible choice. RF times RF. Got it? And then where do we look next? Sign of the last term, and that's positive. That tells you these two have to be the same, and since the middle one's negative, they both have to be minus. Can you think of two numbers that multiply to be 10 and add to be 11? 10 and 1, that's all. Okay, so your first rate is either 10 miles per hour or 1 mile per hour, right? Whoops. What is my H's are looking like R's, miles per hour. Okay. Now, do you think it makes sense for the rate of the first leg to be 1 mile per hour? Hint, the rate of the second leg is less than that? No, that means you're going backward on the second leg. You're never going to finish that race. So I think we can throw out the 1 and just use the 10. So it looks like the rate of the first leg is going to be 10 miles per hour, and the rate of the second leg is going to be 8 miles per hour. And it's real easy to go check it. Just do the math, okay? And let's see if that's what they get. So the rate of the first RF is equal to 10 miles per hour, and the rate of the second, I'm going to call it that now, is RF minus 2, which is 8 miles per hour. Okay, let's just see. If we do 10 miles per hour for the first 20 miles, that's going to be 2 hours to do that part. And do 8 miles per hour for the next 16 miles, that's 2 hours for that part, and 2 plus 2, 4. Didn't know you'd be doing such high-level math today, did you? Okay, 2 plus 2 is 4. It checks. Okay? So, all right for me to erase? Are you still writing? Okay? Erase? Okay. Now, let's see how they do it. All right. The rate for the first 20 miles, they just called it R. They were real cheap. They didn't want to call R sub F. Okay. For the next 16 miles was R minus 2, which is perfectly fine. It's correct, just like we did without the F's. Okay. And then the time was the distance divided by rate, 20 over R. The time for the second 16 miles, the next leg, was 16 divided by R minus 2, just like we did. And then we know the total time was 4 hours. So 20 over R plus 16 over R minus 2 is equal to 4. Good for them. They got it right. Then what we're going to do is the least common denominator is R times R minus 2. There's no common factors here, so you just have to multiply them together. Multiply this by this one, and by that one. And that gives us on the next page. R minus 2 times 20 plus 16R is equal to R squared minus 2R times 4. Now, why they did it that way, I don't know, but it's fine. Oh, I know why. They can divide out the 4 more easily. No, they didn't. They multiplied it through anyway. Never mind. So that would be 20R minus 40 plus 16R is equal to 4R squared minus 8R. Same thing we got, except we had F's in there, right? Okay? Then they combined like terms. That gave them 36R minus 40 is equal to 4R squared minus 8R. And then we moved everything to the right-hand side, just like we did, and get the same equation, 4R squared, 0 is equal to 4R squared minus 44R plus 40. Look at that. And then they divided out the 4, or factored out the 4, and then, lo and behold, they divided it out and got rid of the 4. That doesn't seem fair, but it's doable. It's an equation. Same as long as you do the same thing to both sides, it's fine. And then they factored that a little further and gave us R minus 10 times R minus 1. So that gave either one of those is equal to 0, so that gave us R equal 10 miles per hour, or R equal 1 mile per hour. Now, if you're doing 1 mile per hour, the rate for the second leg would be a negative 1 mile per hour. They're moving backwards. Not very good. Not going to work. So we're going to use the first one. R is equal to 8 and 10 and 8. So the solution, R equal 1, is not possible because the rate in the last 16 would be minus 1 mile per hour. Never going to get there, okay? Going to move backwards. So the rate for the first 20 miles was 10 miles per hour. For the next was 8 miles per hour. Okay. Do I hear some rumbling around? What could that possibly indicate? That we're almost out of time, aren't we? But we also, if I'm not mistaken, we just finished. There is a check your understanding number 2 that has a solution back at in just a couple pages here, and then you have 2 practice problems. Please do all 3 of those. And that, folks, does finish section or module 12. So, what say? Ready for the test on Monday? What you say? Yay? Yay! Okay, we will do the test on Monday. Okay.
Take either of these.
What's that now?
When you get it to, does it have to be in that way, or does it matter?
No, either way is fine. That is perfectly correct, and I didn't see the minus sign at first. Yeah, as long as you have the minus sign there, both of those answers are absolutely correct. We have a sign, or yeah, I may say they're not, but they are. Okay. I wouldn't either if I were. No. Okay. Good deal. So we'll have the test on this module on Monday. Thank you so much. That's right. You're doing what?
Having trouble getting to your book.
To
The book for this class.
Oh.
Like for reader from home.
Right.
Like, this is, like, I bought it like a long time ago. I bought September 6th.
Right.
And I bought it like 2 years. Yeah.
Right.
And like, it tells me to go to home, and once I go to home, it's asking for your instructor key or something like that.
Okay. Let's see. I gave it to you at the first of the term. There it is.
That's the one for the book?
I don't know. It's the only key I have.
Okay. I'm going to take a picture.
Okay.
That'll be easier for me. Because I've been having trouble with the quiz, and I've been trying to go back on. Also, how do I get to your YouTube thing?
Okay. Do you know how to get to Blackboard?
Roger that.
Okay. In this course.
Yes.
Okay. Now, when you get to this course in Blackboard, at the home page, there's going to be a huge column of blue tabs here.
Okay.
Okay. Just to go over all of them. Somewhere near the top is one that says something about, maybe about the syllabus or something like that. That's where the syllabus is.
Okay.
Then either one below it or shortly below it says something about the instructor information. That's where my locator card is.
Right enough.
All the rest of the stuff is down. It's about 2/3 of the page down or something like that. And it says class handouts and more.
So
You
now,
click on that, you'll see all the PowerPoints are in there. You'll see some websites that people have given me or I found myself. And you'll see somewhere down there, I think at the very end, something that says YouTube videos.
Okay.
Math 100 YouTube videos. Click on that, you'll see them all. Now, some of those that don't talk about modules in these chapter numbers, those are from the old thing. That's going to be at the top. Scroll on down, and when you see these start picking up, and you're looking for the ones now probably from module 12. So,
okay.
yeah, there'll be 12 point this, that, and the other.
Thank you so much.
All right, glad to. Yes, sir.
Good morning.
Morning. Okay.
I've been working on test 5.
Okay.
I have a question.
Okay.